Welcome to the deep dive. Today, we're taking a slightly different approach. We're not focusing on specific findings necessarily. Instead, we're looking at the blueprint, the structure behind psychological knowledge itself.
Yeah, the how-tos. We've gathered some really foundational source material. It walks through how a researcher goes from just a basic idea
Right.
to a testable hypothesis, figuring out what the results mean, and crucially, making sure the whole process is solid.
Our mission today is pretty straightforward. Give you a shortcut, really, to understanding how psychological research actually works.
It's about knowing the rules of the road.
Yeah.
And by the end, you'll definitely know the difference between a study that just suggests a link and one that can actually claim cause and effect.
Which is, honestly, knowledge you can use every single day, especially when you see those science headlines pop up.
Absolutely.
So let's start with maybe challenging a stereotype, that image of a scientist.
Oh yeah, the old white man in a lab coat cliche.
Exactly. It's still so pervasive. But our source highlights a fantastic counterexample. Dr. Kizzmekia Corbett.
Right, an African-American woman, key researcher behind the Moderna COVID-19 vaccine.
And she specifically said she was determined not to be a hidden figure.
Which is powerful. But it also points to something deeper, doesn't it? People have these expectations about the person doing science, and they often misunderstand what science itself actually is.
Totally. There's this idea that because psychology studies, happiness or anxiety, it's somehow softer, less rigorous than physics or chemistry.
But the source material is really clear on this. A field is scientific not because of what it studies. Could be planets, could be butterflies, could be human connection.
Doesn't matter.
It matters how it studies it. Psychology is a science because it uses the scientific method rigorously.
Okay, let's unpack that then. What are the actual steps, the mechanics of this method?
Well, it's maybe best to think of it as a cycle, a kind of five-step loop that keeps pushing knowledge forward. You start with step one, observing some kind of phenomenon in the world.
Just noticing something.
Yeah. Then step two, formulating a hypothesis and predictions. This comes from your broader theory about why things work the way they do.
Right.
Step three is testing that hypothesis through empirical research, actually collecting data.
Okay, data collection.
Four is drawing conclusions based on what that data shows.
Excellent.
And then step five is evaluating the theory. Did the data support it? Does the theory need tweaking? Which naturally leads you back to more observation. Step one again.
So it's continuous. Observation sparks a theory like the source mentions the theory that belonging to a social group is maybe the most fundamental human need.
Exactly. That's the broad idea. From that, you derive a hypothesis, a specific testable guess. Like if belonging is key, then maybe doing something for your group feels good.
And the prediction is even more specific.
Super specific, like participants who spend money on others will report higher happiness scores at the end of the day than those who spend it on themselves. Testable.
Gotcha. And the source has that great example from Dunn, Acton, and Norton.
Yeah, the giving versus receiving study.
The observation was simple. Feels good to give someone a gift, right?
Right, which led to the hypothesis. Spending money on others boosts happiness more than spending it on yourself.
So they tested it. Randomly gave people $5 or $20, told some to spend it on themselves, others to spend it on someone else. And the conclusion, spending on others' group was happier that evening. It supported the hypothesis.
A nice, clean example of those first four steps. Observation, hypothesis, test, conclusion.
But hang on, before you can even run a test like that, you have to deal with the fuzziness of concepts like happiness.
Yes. The operational definition. This is absolutely critical, maybe the most critical step for clarity.
Okay, explain that.
So a variable is just anything that can change or vary. Obvious enough.
Like happiness level or amount of money spent.
Exactly. An operational definition is the concrete, specific, objective description of how you are going to measure or observe that variable in your particular study.
You have to nail it down. You can't just say, we measured happiness. How?
Precisely. It eliminates the vagueness. And the source shows how different these definitions can be, even for the same concept.
Right. Like, happiness could be defined as a score on a specific questionnaire, the satisfaction with life scale, maybe.
Or you could skip self-report entirely. That Harker and Keltner study defined happiness by analyzing Duchenne's smiles. The genuine eye-crinkling kind in old college yearbook photos.
Wow, that's specific.
Super specific. And they use that physical measure to predict positive life outcomes decades later. It shows the power of a good operational definition.
Okay, so that's the bridge. Abstract idea to concrete measurement. Once we have that, the method leads us down different paths, right? 3 main types of research.
That's right. Descriptive, correlational, and experimental.
Let's start with descriptive. Sounds simplest.
It is. Its goal is just to describe the basic features of something. How common is it? What does it look like? Think methods like systematic observation, interviews, surveys.
Okay, just getting the lay of the land.
Yeah. But even here, there are pitfalls. With surveys, for example, you always worry about socially desirable responding.
People fibbing to look good.
And the source also mentions case studies that really deep dive into one individual, like Erik Erikson studying Mahatma Gandhi.
Fascinating stories, but you have to be careful about generalizing, right?
Absolutely. What's true for Gandhi? Probably not true for most of us listening.
Still, descriptive work can give us important baselines, like that research on happiness in non-industrialized cultures, the Inuit, Maasai.
Yeah, finding that even with vastly different lives, most people tend to rate themselves as pretty happy, above the midpoint on satisfaction scales. That's a solid descriptive finding.
But if you want to know if happiness changes alongside something else, like income,
then you move to correlational research. Now we're looking at how variables are related, how they change together, correlated.
and that relationship gets a number, the correlation coefficient.
Yep. Ranges from -1.00 to +1.00. The sign tells you the direction. Positive means they move together both up or both down. Negative means opposite directions, one up, the other down.
Like more study time, higher grades, that's positive. More missed classes, lower grades, still positive because they move together in the same direction conceptually, even if it's downward. Wait, more missed classes, lower grades would be negative, right? As missed classes go up, grades go down.
Ah, good catch. Yes, exactly. More missed classes leading to lower grades is a negative correlation, important correction. And the number tells you the strength. Closer to 1 or -1 is stronger. Closer to 0 is weaker.
Okay, but here's the big warning label, right?
Here's where it gets really interesting, yeah. And where you, the listener, need to put your skeptic hat on every time you read a news headline about science.
Because
Say it with me. Correlation is not causation.
the classic causation trap.
It gets people every time. The textbook example is always ice cream sales and crime rates.
Right, they often show a strong positive correlation. More ice cream sold, more crime happens.
So does ice cream cause crime? Obviously not. There's usually a third variable driving both.
In this case, heat. Hot weather makes people buy more ice cream, and it tends to make people more irritable and likely to be outdoors, potentially increasing crime rates.
Exactly. The heat is the confound, the third variable. So correlation alone can't prove one thing causes another.
So if it can't prove cause, why do we even bother with correlational studies? Are they just flawed?
Not at all. They're incredibly valuable. First, for prediction. We know GPA is correlated with college success. It predicts it pretty well. But nobody thinks the GPA caused the success, right? It's just a useful indicator.
Okay, prediction is useful.
And sometimes it's the only ethical or practical option. You can't experimentally assign people to experience things like aging or being a certain gender or living through a pandemic like COVID-19. Correlation lets us study these important real-world factors.
That makes sense. And researchers are getting cleverer with it too, right? Longitudinal designs.
Yes. Following people over time is a big step up. Measuring variables repeatedly lets you see if changes in one thing precede changes in another. That nun study is just wild.
The one looking at their journals from when they were young.
Yeah, written at age 22. The amount of positive emotion expressed then predicted a 2.5 times higher chance of being alive 60 years later. That time element gets us closer to suggesting causality, though still not proving it.
And now we have big data feeding into this too.
Huge boost. Using public records, birth certificates, diplomas, or even analyzing language on Twitter or images on Instagram lets us do correlational studies on a massive scale.
Like linking county-level data on racism to infant mortality rates.
Powerful associations. Important for identifying potential problems and making predictions. But still, to actually prove cause and effect.
You need the gold standard, experimental research.
The experiment. That's the only design that lets you truly nail down causation.
So what defines an experiment?
It's a very carefully regulated procedure where the researcher manipulates one or more variables they think are the cause.
That's the independent variable, the IV.
Right. And then they measure the effect of that manipulation on some outcome variable.
The dependent variable, the DV, cause and effect.
And the absolute linchpin, the technique that unlocks causal claims, is random assignment.
This is huge. You have to assign participants to different conditions purely by chance.
Yes. Flipping a coin, using a random number generator.
Yeah.
Whatever it takes. This ensures that, on average, the groups start out the same on all pre-existing characteristics: motivation, intelligence, mood, everything.
So any differences between the groups after the manipulation must be due to the IV, because that was the only systematic difference introduced.
That's the logic. It isolates the causal factor.
Like that King study you mentioned earlier, 5V was mood-induced by happy or neutral music. DV was ratings of meaning in life.
Because they used random assignment, they could confidently say the happy music caused the higher meaning ratings in that group.
And you always need a control group, right? The comparison group.
It's essential. They get treated identically in every way except for the IV manipulation. Maybe they hear neutral music or get no music. That comparison shows the effect wasn't just due to, say, being in a study or listening to any music.
Oh, okay. But sometimes random assignment just isn't possible, ethically or practically.
Right. And that's where you get quasi-experimental designs. They look like experiments, but lack that random assignment.
Like studying soldiers who saw combat versus those who didn't, you can't randomly assign people to experience combat.
Exactly. So while you can compare the groups, you can't be as certain that the combat caused any observed differences because the groups might have been different to begin with. Causal conclusions are much weaker.
Okay, so we've got the ideal setup with experiments. But even a perfect design can get messy because, well, humans are involved.
Which brings us to validity and bias.
Validity is about whether the study is sound, right? Two types.
Yep. First, external validity. Do the findings actually generalize to the real world, outside the lab?
Like, if your lab study uses loud noises to simulate stress, is that really the same as, say, financial stress or relationship stress? Maybe not.
That's the question of external validity. And then there's internal validity. This asks, was the experiment designed and conducted properly? Is the change in the DV really due to the IV, or could something else be going on? Are there biases?
And biases creep in easily, like experimenter bias.
Yeah, where the researchers' own expectations subtly influence how they treat participants or interpret data. Rosenthal's classic maze-bright rats study is the perfect example.
Students were told some rats were genetically superior, even though they weren't. And guess what? Those rats performed better, likely because the students treated them differently.
Expectations became reality. And the flip side is research participant bias.
Where the participants try to figure out what the study is about and act accordingly.
Or just act in ways they think will make them look good, or please the experimenter, sometimes called demand characteristics.
And the most famous participant bias is probably the placebo effect.
Absolutely fascinating. Just the expectation of receiving a beneficial treatment can actually produce real effects, even if the treatment is inert, like a sugar pill.
Which is why medical trials absolutely need a placebo control group.
And psychological studies, too, often. To counter both experimenter and participant bias at the same time, the best defense is the double-blind experiment.
Okay, double-blind means?
Neither the participants nor the person administering the treatments or collecting the data knows who is in the experimental group and who is in the control, or placebo group.
Like in the big COVID-19 vaccine trials the source mentions. Critical for objectivity.
Keeps everyone's expectations from muddying the waters.
Yeah.
It's the gold standard for internal validity.
Okay, so we ran our carefully designed, maybe even double-blind study. We have the data. Now what? Statistics time.
Math time. Two main flavors, descriptive and inferential.
Descriptive just describes the data.
Summarizes it. Tells you what you found in your sample. We use measures of central tendency first.
Like the mean, the average score.
Yeah, the average. But the mean can be really misleading if you have extreme scores or outliers.
Ah, right. The example of average income in a town where one person is a billionaire. The mean makes everyone look rich.
Exactly. So often the median, the literal middle score when you line them all up is more representative, especially for things like income. Or sometimes the mode, the most frequent score.
Okay, so mean, median, mode tell you the center. What else?
We need to know how spread out the scores are. That's measures of dispersion or variability. The simplest is the range, highest minus lowest. But the most common and useful is the standard deviation.
Standard deviation. That tells you, on average, how much scores tend to differ from the mean.
Precisely. A small standard deviation means scores cluster tightly around the average. A large one means they're more spread out. Gives vital context to the mean.
Okay, that's describing the data. Then inferential statistics.
Inferential stats help us draw conclusions. They're tools to decide if the results we found in our sample are likely to be real statistically significant, or if they could have just happened by chance.
Trying to generalize from the sample to the larger population.
Right. And historically, the magic number has been the 0.05 level of significance.
Meaning researchers were willing to accept a 5%, or 1 in 20, chance that their finding was just a fluke, a random occurrence.
Yep. But that 0.05 standard is now right in the middle of the so-called replication crisis in psychology and other fields.
Because a lot of studies published as significant aren't replicating when other labs try to repeat them.
Exactly. The source points out that the intense pressure to publish significant findings might have encouraged questionable research practices, sometimes called p-hacking, tweaking data, until it crosses that 0.05 line.
And now there's a serious push to make the standard stricter, like 0.005.
There is a much lower tolerance for chance findings. It's a major debate within the field.
You know, the fact that scientists are questioning these fundamental statistical tools, it makes you think about the origins of these tools themselves.
And that requires a serious pause. The source brings up a really critical controversy here. The actual founders of many of the statistical methods we rely on, names like Galton, Pearson, Fisher, they were prominent eugenicists, white supremacists, deeply problematic figures.
Wait, seriously, so the tests we use to analyze data, they were developed by people with those beliefs?
Many were developed in part within that context, to try and quantify and, in their view, prove supposed differences between groups, often based on race, to justify social policies.
Wow, that's unsettling.
It is. The math itself might be neutral, but its development and initial application were tangled up with non-objective, harmful social agendas. Statistics provide this powerful appearance of objective truth. And we have to acknowledge that history. We have to recognize that science, including its tools, always exists within a set of social values and carries historical baggage.
That really underscores the need for critical thinking when we encounter research findings. Given all these potential issues, biases, replication problems, even the history of the tools, how should we as learners approach this information?
Great question. The source offers several crucial guidelines for being a wise consumer of psychological science.
Okay, let's hear them.
First, avoid overgeneralizing, especially from limited samples. Remember how early stress research only used men? That's a classic example.
Or the weird sample problem, Western, educated, industrialized, rich, democratic. Most research uses participants like this.
Exactly. You can't automatically assume findings from, say, American college students apply to everyone on Earth.
Good point. What's next?
Second, and this is vital for you personally, distinguish group results from individual needs or experiences.
The average isn't the individual.
Right. Statistics might tell you the average 2-year-old says X number of words, but maybe your kid doesn't. The source mentions Albert Einstein didn't talk until age 3. Group data describes trends, not individual destinies.
Okay, don't overgeneralize. Distinguish group from individual. What else?
Third, look beyond a single study. Science is cumulative. Real answers emerge slowly through lots of studies, through replication, through researchers building consensus. One experiment is never the final word.
So be wary of breathless headlines about one breakthrough study.
Definitely. Fourth, always question claims of causation in media reports. Unless you know for sure it was an experiment with random assignment, the most they can claim is correlation, a link, maybe a prediction, not cause.
Got it. Correlation isn't causation. Drill that in.
And finally, consider the source. Where is this information coming from? A peer-reviewed academic journal. That's the highest standard. Reputable news source. Okay. Tabloid. Sketchy social media feed with no author. Be highly skeptical.
Solid advice. Check the sample, check the individual relevance, look for multiple studies, demand experimental evidence for causation, and check the source credibility.
That's the critical thinking toolkit.
And the source gives a great example of how science progresses using these principles. James Pennebaker's work on expressive writing.
Yeah, it's a perfect illustration. It started with a correlational observation.
He noticed people who'd lost someone to suicide often didn't talk about it, and they also seemed to get sick more often. A correlation between bottling it up and poor health.
But correlation isn't causation. So next step, the experiment.
Right. He randomly assigned participants. Some wrote about their deepest trauma, others wrote about neutral topics.
And the results. The group that wrote about trauma showed better physical health markers, even improved immune function months later compared to the control group.
Boom. Random assignment allows the causal claim. The act of writing about trauma caused health benefits.
And it didn't stop there. Meta-analyses combining results from many studies confirmed these benefits across thousands of people. It's now established knowledge. Though interestingly, later work showed writing about positive things like gratitude or future dreams can also be beneficial.
C. Science evolves. Observation, correlation, experiment, replication, extension. That's the process.
It really highlights that the whole thing, from noticing something interesting to designing studies, even arguing about stats and replication, it's all an ongoing conversation, a self-correcting process, ideally.
And it reminds us that even when a finding is statistically significant and comes from a good source, it's still just one piece of the puzzle. Critical thinking is never optional.
Absolutely. Which leads nicely into our final thought for you today.
Okay, let's hear it.
If scientists themselves have to constantly question and reevaluate their own methods, their own tools, like the p-value standard we talked about, then how should you approach the knowledge you gain? Especially knowing that future research might refine or even overturn the theories we hold today.
It's a call for intellectual humility, maybe.
And active engagement. So our challenge to you is this. Take one health claim or one psychological finding you see online this week. Apply those critical thinking rules we discussed. Ask, what's the sample? Is it group versus individual? Is it just one study? Are they claiming causation without an experiment? Who is the source?
Really put it through its paces.
Exactly. Stay curious, stay critical.
And we'll catch you on the next deep dive.